First law of thermodynamics. So, I like that response. So we're going to talk about what a thermodynamic system is. It's basically a system, but in the context of thermodynamics. We'll talk about work done again. So remember, how did we calculate work last time we talked about work? Well, kind of, yeah. That's one of the options. If you have a graph, how did you calculate it?
The area under the force curve.
Yes, the area under the force curve. What kind of graphs are we dealing with now? What are the axes?
Temperature.
Pressure?
Yeah.
Pressure and volume. Okay? So it'll still be the area under the curve, but it'll be the area under the PV diagram curve. Okay, so we'll talk about why that is in a little bit. Talk about paths between thermodynamic states. That's just the lines that connect the dots on the PV diagram. Internal energy. Remember, internal energy is the same as thermal energy. So that's any of the stuff that we treat as measurable by temperature. Okay. And then we have kinds of thermodynamic processes. We've already talked about some of these, but we're going to go into a little bit more detail about the math and how we get back and forth between them. And ideal gas, ideal gas, ideal gas. All right? All right. We can do this today. So let's talk about a thermodynamic system. Here is a thermodynamic system. Anybody know what this is? Yeah, it's a popcorn kernel. Okay? So what do you put into the system? Heat. All right? So you put heat into the system. All right, that means hot oil, right? So you want to do like the movie style, you do the hot oil, or you just put it in a microwave and then you add heat by vibrating the stuff inside of it, okay? Then work done by the system, okay? Because, right, the popcorn kernel is a sort of a hard container. Once you get it hot enough, what does it do? Explodes, okay? So pressure builds up inside of the kernel, it pushes the shell out, and then you have a tasty snack, okay? So you add heat, that means there's work, and that is your thermodynamic system, all right? Now here you'll notice the boundaries of the system don't have to stay the same shape and size because the popcorn kernel, once it explodes, that's still the system, but now it's bigger, okay? So let's talk about work done during volume changes. So if you change the size of your system, that's a change in volume. All right, so remember, this is what work used to look like. So we have this force versus displacement, or force versus position graph, okay? So if you graph force versus position, it looks like this. If you want to know the work done from here to here, what do? Take the integral, which means figure out the area under the curve, okay? So that's the work, all right? Now let's talk about what we're using in thermodynamics. So we have a PV diagram. Let's say we have one that looks like this. So here's our PV diagram. What kind of process is this? Which thing's not changing? PV, T?
Heat's changing. Or pressure's changing.
ISO what?
Isobaric?
No, because that would, isobaric would be flat.
Oh, okay.
Isochoric would be vertical. This is the other one, isothermal expansion, okay? So this is an isotherm. You see this like inverse curve looks like an isotherm, and then it's an expansion because it's going from a smaller volume to a bigger volume. It's going this way along the volume axis, okay? So here's your isothermal expansion, all right? So how are we going to calculate work? Well, let's go back to what we had before, okay? Work was F dot dx. Okay? What do we know about pressure? How do we define pressure? Force over area. Okay? So the force divided by the area gives you pressure. So if you have force, you can write it as pressure times area. Okay, it's just rearranging things. So we end up with the integral of pressure times area dx. Okay, if you take area and you multiply it by another length, what do you get?
Volume.
Volume, right? This is meters squared, this is meters, now you have meters cubed. This becomes PdV. Okay? Which means, if you have a PV diagram, how do you find the work? Yeah, area under the curve. Okay? So the work done by the gas, right? The force is the gas here. You can see it's doing work. It's the gas is pushing the piston this way. So the force is this way, the displacement's this way. That should be positive work. Okay? And you can calculate it from this graph by looking at the area under the PV curve. All right? So just like work before, work's going to be positive and negative in the same way. So if this were an isothermal compression, would work be positive or negative? Negative, okay? Because the outside, right, the force from outside, the pressure from outside would be doing work on the system. It would be pushing the piston in, okay? In this case, because the gas is pushing the piston out, it's doing the force, okay? And then it's going in the same direction as the displacement for the system, all right? So yeah, you can see, just like before, you're looking at force in the direction of dx, and this is your work. So this is the work done by your system, all right? The work done by the environment would be the force pushing this way, okay? This is the force from your system, this is the force from your environment. Depending on whether those are going in the same direction as your displacement tells you whether you have a positive or negative work. Yes?
For isothermic, is the pressure always constant?
Does it look like it's constant?
No.
So for isothermal, pressure and volume change and only temperature stays the same, right? And you can see here at the initial point we have a pressure and volume that's different from our final pressure and volume. Yeah. The only thing that stays the same is temperature. It's a good question. All right, so this is what I'm talking about. Here we have, this is the force from your gas, right? It comes from inside where the gas is. This is the force from the environment. It comes from outside. Depending on which force you're talking about, depending on which work you're talking about, right? Work system goes one way, work environment goes the other way. So let's say we wanted to have a compression, okay? That means we've changed the direction of this arrow. The curve's the same. We're going from the same, between the same two states, but now we're going in a different direction, okay? So it's still the same area, but what is your work in this case?
Negative.
Negative, okay? So if you go this way, it's going to be positive. If you go this way, it's going to be negative. And that's the work done by the system, okay? What's the sign of the work done by the environment? Positive, okay? So it's just a matter of, just like before, is your force going in the same direction as your displacement? All right? So remember, whatever your work system is, the work environment's going to be the negative of that, okay? Because these forces always oppose each other, so you just have to figure out which one you're talking about. All right. Here's a question. We're mostly thinking it's either positive, negative, or zero. So please discuss, and we'll put again. Better, yes. Zero, huh? So the work done by the system is going to be integrated from here to here. That's going to be a positive value, okay? And I just want you to remember, anytime you have an expansion, right, that means the work done by your system is positive, because the way to expand the volume of the piston is that the gas inside has to push the piston. So if the gas is displacing the piston, it's always going to be positive. Yes?
But if there's no increase in the pressure, then how is there an increase in volume?
Well, there's probably an increase in temperature, and as you do that, if you do that nice and slow, right, there'll be a microscopic increase in pressure, but then the volume changes. And so we treat that as though the pressure is not changing, although I think if you measure it at like a small enough scale, you'll see there's minor pressure changes, but then it compensates, right? So, yeah, it's a little bit more complicated than that. Okay, here's another question. Okay, let's just. Okay, one more person got the right answer. So, which way are you? What are you? Are you the system or the environment? You're the environment. Which way are you pushing? Down. Which way is the piston moving? Down. Okay, so that means the work done by you, the environment, is positive.
Oh.
All right, the gas pushes which way? Up. Right, the pressure is always going out in all directions. So the gas is pushing the piston up, but this is being displaced down. So if it asks for the work done by the system, that would be negative. Okay, so since you're the environment, you're moving in the same direction as the displacement. The environmental work is positive. Okay, system work would be negative, but you have to be careful because we're going to start switching back and forth between work done by the system and work done by the environment. So you have to pay attention to which one it's asking about. Okay, all right. Fun physics news, by the way. Remember how we talked about the kilogram? The kids ganged up on me last night. Oh, well, we're not that good, so let's try again.
Probably need to.
Okay, we're thinking. So I just want you guys to think about what these graphs look like. Okay? So if we have a PV diagram, what does an isobaric curve look like? Straight, right? So that's going to have work that looks like this. Okay? What about an isotherm? It looks like this.
Isobaric.
So you can take an area under that, it's going to look like this. All right? What about an isochoric graph? That's vertical. What's the area under that? 0. Okay? So isochoric, there's no work, right? Because remember, every time we're doing work, we're talking about this piston, it has to change volume, right? The gas has to either push the piston up or the environment has to push the piston down. But if you don't change volume, the piston doesn't move. The piston doesn't move, the displacement is 0, and the work done is 0, okay? So how are we changing, if we're not doing work, how are we changing things like temperature or pressure? What other things do we have to work with? Well, we have work plus heat. What's the other one? Well, there's work and there's heat, okay? You can add temperature with heat. You don't have to use work, okay? So if you want to change the temperature, you can just light a fire, all right? And that's not doing physical work, that's just adding heat to the system. Or you can put it on ice, and that's taking heat out of the system, okay? In an isochoric change, pressure and temperature change, right? So yeah, isochoric, pressure and temperature change, but volume is constant, right? In isothermal, pressure and volume can change, but temperature is constant. Isobaric, pressure stays the same, and temperature and volume can change. Yeah, okay. So isochoric, okay, that's the only one where work is 0. All right, let's try this. And if I say work done on the gas, is that work done by the system or work done by the environment? Environment, okay. Work done on the gas is the environment. Work done by the gas, that's the system, okay. Okay, so 2 things to remember when doing this. One, an integral is the area under the curve. So, well, before we start, is this going to be positive or negative work? Is it? Negative, right? Because this is the environmental work. Okay, so this is the work done by the environment. So that means whatever you get from this integral, you have to add a negative to it because what the integral gives you is the work done by the system. Okay, so if you integrate from here to here, that'll give you the work done by the system, and we know the work done by the environment is just the negative of the work done by the system. Okay, so in order to integrate, we just want to take the area from here to here, so all of this. Okay, and because this is a nice geometric shape, you can do this geometrically. There's lots of different ways to go about it, but we'll just do one. So break this into a triangle, so this piece, this didn't work out properly. Pretend that's straight. Okay, and then this rectangle. Okay, so we'll start with the rectangles. What's the area here?
Base times height.
Base times height. So that would be 500
Well,
centimeters cubed. Okay, now remember, we need these things to be in meters cubed and pascals, okay, in order for our units to work out correctly at the end. So if this is base times height, that's 500 centimeters cubed. How do we get meters cubed? Times 10 to the what? 10 to the negative 6, right? Because remember, there are 1,000,000 centimeters cubed in 1 meter cubed. So this is going to be times 10 to the negative 6 meters cubed. Okay? And then what's our height? Yeah, that's 300 times 10 to the third pascals. Okay? So 500 times 10 to the negative 6 meters cubed times 300 times 10 to the third pascals. What does that give us? 150. 150 joules. Okay. What about over here? Okay, that's still the same base, right? 500 times 10 to the negative 6 meters cubed times the height, which is 100 times 10 to the third pascals. Okay. What does that give us? 50. Okay. 50 joules. And then we do this one. And the only thing you have to remember here is this is a triangle, so you have 1/2 base times height. So that's still 500 times 10 to the negative 6 meters cubed, and then 200 times 10 to the 3 pascals. Okay, and that's going to give us another 50 joules. All right, the total work done by the environment, you know this has to be negative 50 plus 50 plus 150 joules. Okay, so it should be negative 250 joules. Right? So you have to keep track of the units. Remember, units for pressure need to be in pascals. Units for volume need to be in meters cubed. So you have to convert anything that you see that doesn't fit there. Okay? And you also have to be careful that you integrate correctly. So that's all the way from the axis to the curve. All right. So let's talk paths between thermodynamic states. We talked about this a little bit in the previous chapter, okay? Remember, if we have a PV diagram, all of these dots represent a state. And what do we mean by a state? What variables do we need to form a state? Yeah, pressure, volume, temperature, okay? And from a PV diagram, as long as you know the number of moles, you can figure out, well, you can just read the pressure and volume, and you can calculate the temperature from PV equals nRT. Okay, so for each of these dots, you can find PV and T, PV and T, PV and T, all right? But a PV diagram also includes how you get from dot to dot, okay? So depending on how you draw these lines, but that tells you what kind of process you use to get from dot to dot. Now we've talked about 3 specific types of processes, and that would be isothermal, isobaric, and isochoric, okay? So constant volume, constant pressure, and constant temperature. Those are not the only ways you can get from one state to another. They're just the most easy to calculate ways, okay? You can go any direction, any curve connecting these two dots is acceptable as long as you can physically do it. All right? And so if you wanted to calculate the work done here, how do you calculate the work done from going from here to here? How much work is done? How do we calculate work on these things?
Area underneath that.
Area under the curve. So you calculate the work from 1 to 2, right, which would just be this area. And then you calculate the work from 2 to 3, which would be this area. And you have to subtract this area from this area because they're going in different directions. Okay? So if you want to calculate the work, you just calculate the work from 1 to 2, and then you calculate the work from 2 to 3, add them together. Okay? It's pretty straightforward. So remember, PV diagram shows how a gas changes from one place to the next. We already looked at this curve, okay? This tells you how you get from one point to the next. This comes from PV equals nRT, all right? And so we want to figure out how to calculate work now. Better. Okay, so the answer is going to be negative, okay? If you integrate from I to F for either A or B, do you get a positive or negative value? Positive, right? But that is the work done by the system, right? This shows the work, if you take the integral on a PV diagram, is the work done by the system. So in order to get the environmental work, all you have to do is flip the sign. Okay, so if this gives you a positive value, you know the work done by the environment is just the negative of that value. Okay, so that's going to be B. Here's another question. Better. Okay, much better. The answer is A. Okay, and remember, the work is the area under the curve. So for A, the work is this, right? That's the area under the curve. For B, that's the work. Which one's bigger? A. Okay. So even though you're going from so remember we talked about when we talked about like conservative forces, we talked about integrals that were path independent. This is not that case, okay? The path you take to get from one state to another matters. The amount of work you're going to do will change depending on how you get from one state to another. Okay, and this ends up being how we calculate things like efficiency of a system. Okay, so if depending on how you design something like an engine, okay, you can get more efficient work out of that system by making sure the paths you take don't do as much work. Okay, or if you, depending on what you're trying to do, if you want the engine to do the work, then you want it to do more work for you. Okay, so that's where we're at. All right, so let's talk about internal energy and the first law of thermodynamics. Okay, so remember we talked about this is the first law of thermodynamics, right? It's change in thermal energy, which we sometimes call internal energy. So thermal energy, internal energy, those are the same thing. Okay. So that's our thermal energy, that's our heat transferred. This is our first law of thermodynamics. There's one other way to write it, because remember, if we change this from environment to system, all we do is change the sign. So this is also a way to write the first law of thermodynamics. It just deals with the other kind of work. Okay? So this is work done by the system. This is work done on the system. Okay? Yeah, and sometimes the thermal energy is called U, which I don't think is a good way to do it because thermal energy is K plus U in the microscopic. So I'd like to use this notation, but don't be confused if you also see it written as a U. All right? Yeah. Especially if you're out in like YouTube video land, there's like lots of different notations people use. So, sorry. Okay, let's try this. Oh. Okay. Well, the answer's changed. So, what's the sign of work? Positive. Why? This is the force from the environment, right? The displacement's this way, so you have positive work, okay? What is Q? Plus, minus, 0. Why is it 0? Insulated, right? So if you're completely insulated, can heat go in or out of your system? No, right? And if heat can't go in or out of your system, what's the only other thing that can change? Temperature, right? Thermal energy is temperature. That's the way we measure it. So if work gets bigger and this is 0, this has to go up, okay? And so this should also go along with your intuition. If you compress a gas, right, and there's nowhere for the heat to go, the temperature has to go up, okay? So in terms of the first law, we're increasing the work done by the environment. That increases the temperature because Q is 0. What happens if we take the insulation away? Then what happens? Then what would stay the same? Yeah, the temperature, right? Then all the heat that's generated by doing the work can escape, okay? So then, what doesn't change? You said temperature, right? So thermal energy is 0, which means whatever work you do is going to be equal to negative heat, okay? The heat leaves the system, the temperature stays the same. Okay, so this is how we use the first law of thermodynamics. This equation keeps track of what's happening. So you have to pay attention to the situation. If something's insulated, Q is automatically 0, okay? Work, you have to figure out if it's work environment or work system and what the sign is. So that's why it's really important. That's what we've been talking about, how to figure out the sign of the work, okay? That's going to affect how you change the temperature, all right? So for instance, in an isothermal process, what's the change of thermal energy?
What's the change in?
Thermal energy. So you have an isothermal process.
There's a change in isothermal energy?
What? So an isothermal process means what? Same temperature.
Yeah.
Okay? So what thing is 0 on here if you have an isothermal process?
Energy. Or
This, yeah,
thermal.
the energy,
Yeah.
right? Because this depends on temperature. So if the temperature doesn't change, this doesn't change, and this is a difference in thermal energy. So whatever it started at, whatever it ended at, so the change is 0. Okay? Your change in temperature is 0. Your change in thermal energy is 0. All right? Which means the work and heat are the only things that change. Okay? What about in an isochoric process? What's 0 in an isochoric process?
Volume.
Out of these things.
Work.
Work. All right? So in an isochoric process, work is 0. Okay? In an isothermal process, change in thermal energy is 0. We haven't learned about when Q is 0 yet, unfortunately. Okay? The other process, the isobaric process, none of these things are 0. Okay? But the nice thing about the isobaric process is it's really easy to calculate work. All right? Because remember, an isobaric process is a flat line. So what's the area under the curve?
Square.
Base times height. Yeah, it's just a rectangle. So P delta V. Okay? So then it's easy to calculate work, but it's not 0. Okay? Remember, isochoric process, work is 0. Isothermal process, change in thermal energy is 0. So you can automatically go to here and figure out the third variable, right? So if you know you have an isochoric process and you know your change in temperature, you can easily calculate heat, right? If you know you have an isothermal process and you can calculate your work, then you can easily calculate heat, right? All right, anyway, so this increases. Here's I don't really like this slide, but it sort of gives you the idea of what's going on with the signs. But we already know all this stuff, so it's just summing up, okay? Here's our first law of thermodynamics, all right? We know if work is done on the system, then your work is negative, right? So if you have some sort of compression, then you have negative work. If you have an expansion, right, if there's work done by the system, if the gas is pushing the piston, then the work is positive, all right? We know if we go heat into the system, Q is positive, heat out of the system means Q is negative. And I'm showing you this because the signs are going to matter a lot when we're using this. And you're also going to have to remember if you're using work done by the environment or work done by the system, because that flips the sign, okay? That's all the stuff that needs to be kept track of. So here's another question. Now we're asking about Q instead of work. Oh man. Okay, so let's talk about this. So we have this situation, okay? Now remember, if you calculate these, this is the work done by the system. Okay, so work done by the environment, this is, A is a larger negative work than B. Okay, so we know work for A is a large negative number, work for B is a slightly smaller negative number. So then we have two other variables we have to worry about. Change in thermal energy, and then it's asking about Q. Okay? What do we know about the change in thermal energy? Well, it's not zero, right? We're going from one temperature to another temperature. Remember, for I, this has PI, VI, TI. So it has the same pressure, volume, and temperature that they start at, and they both end at the same pressure, volume, and temperature, but they're not the same, like I and F don't have the same pressure, volume, and temperature. Well, they have the same pressure, just about, okay? But because each of these dots represents a state, we start and end at the same state, okay? So that means our change in temperature is the same for both gases, which means our change in thermal energy, it's not zero, but it's the same, okay? So for instance, if our change in thermal energy was 10, okay, let's say work for A is -2, and work for B would be something smaller, so -1, okay? That means our Q for A would be 12, and our Q for B would be 11. All right, because they both have to add up to the same number. And so since this is a larger negative value for A, it has to be a larger positive value when you're talking about Q for A. All right, so the answer is going to be A. All right, you're just balancing this equation. This is the same for both process A and B. These are different, and you can use that to calculate Q. Yes?
Is it true to say the statement more work, more heat?
As long as thermal energy doesn't change. Right? So, yeah.
So this is isothermal.
It's not. If it's isothermic, then change in thermal energy is 0. This is a change in thermal energy that's just a constant for both processes. Okay? So as long as you start and end at the same point, delta E thermal is the same for each process. If it's an isotherm, then it's also 0. Okay, yeah. No, I know it's confusing. Okay, let's take a break. Come back in about 10 minutes. That would be 9:07-ish. All right.
Alright, you said something about the large dot. But I didn't Q. So it makes Q different.
No, thermally isolated makes it 0. Insulation makes it 0. The water bath makes delta T 0. Think about it this way. You go from the ocean, what temperature is it going to end up?
I did that thing. I didn't use it in a while. I woke up on the couch.
So if you're in contact with a large water bath, that maintains the temperature. So delta T is 0. If delta T is 0, which of those variables is 0?
Maybe I had it on TV to watch like Sunday Night Football, and I woke up this morning at like, no.
Change in thermal energy depends on temperature. If you don't change temperature, you don't change temperature.
Yeah, dude, shoes on, clothes on, I just scratched up.
work, and then
Faster.
what?
That's all I know.
All right, let's talk about this. So we start with a warm drink in a glass bottle and we put it in the freezer. Okay, we're assuming this bottle is sealed. Okay, so what does not change? Which variable does not change? Well, that's it. Work is 0 because which variable doesn't change? What kind of process is this? Isochoric, because the bottle stays the same volume. Okay, and if volume doesn't change, that's isochoric. That means work is 0. Okay? What about heat? Is it going in or out of your system? Out. Is that positive or negative? Negative. Okay, so heat's going out of your system. That's negative. What happens to the temperature? It goes down. So that is a negative change. Okay, so your change in thermal energy is negative. Your heat is negative because heat's leaving the system, and your work is 0. Okay? All right, for the next one, you compress a gas which is thermally isolated from its surroundings. What does thermally isolated mean?
You can't go in or out.
It means heat can't get in or out. So usually that's like a thermos or a cooler or some sort of insulation. Okay? If heat can't get in or out, that means which of these variables is 0?
Q.
Q. Okay, so Q is 0 when heat can't go in or out. All right? Which means Q is also 0 in C, right? That also says it's thermally isolated. All right? So for B, you're compressing a gas. Remember, we're talking about the work done by the environment. So if you're compressing a gas, the environment is pushing on that gas. Okay, is that positive or negative work?
Positive.
Positive. The environment is doing the work, so that's positive work, which means the change in thermal energy should also be positive. Okay? Here you're expanding a gas. That means the work done by the environment is
Negative.
negative. Okay? And that means your change in thermal energy should be negative. Okay? Yes?
Why is expanding a gas negative work?
Because that means the force is coming from the gas, which means it's going, the displacement is this way, and the work done by the environment is this way. Right? So if you think about a system with a piston, okay? The environment's trying to push down, but the piston's moving up if it's expanding. That means your force and your displacement should be opposite, and that's negative work. Okay? So that would be positive work done by the gas, but it's negative work done on the environment. Okay. And let's say, so you very slowly compress a gas which is in thermal contact with a large water bath. Now, whenever you see slowly and large water bath, what kind of process should you think of? Yeah, isothermal. Okay, an isothermal process, which means the temperature doesn't change, which means which of these things is 0?
Temperature.
Yeah, the change in temperature is 0, and the change in thermal energy is 0. Okay? If you're compressing, what does that mean about the work?
Work should be positive.
Work should be positive because you're pushing down on the piston and it's moving down. Okay, so positive work. What does that mean about Q?
Negative.
Negative, right? Heat should be leaving the system as you compress it in order to maintain the same temperature. Okay? All right. So that's how the first law works. All right? So here's a fun fact. Let's say this is our first law. Okay? If we have a cyclical process, meaning we start and end at the same point, what does that tell us about our change in thermal energy? 0, right? Because at this state, pressure, volume, and temperature are the same. So you've changed them as you go over here, but once you get back here, the temperature is the same temperature you started with. So for all cyclical processes, change in temperature is 0, which means change in thermal energy also 0. Okay? So that means for any cyclical process, the work done by your system, meaning the area inside this curve, is equal to your heat. Okay? So the work done by the system is equal to the heat. And if you want to actually calculate the work, right, you integrate this way, and then you integrate that way, and the work is just the area enclosed in the cycle. All right? So this is the work done by the system, and it should be equal to the heat because we know our change in thermal energy is 0. Right? We start and end at the same process. And why is it useful to have cyclical processes? Think about your car, right? How does a car engine work?
With pistons?
Yeah, the pistons, right? It cycles. So it starts at one point, and it comes back to that point, and then it starts over. If it only did that once
Oh, yeah.
and ended at a different point, how far would you be able to travel?
Flintstones.
Not that far, right? So you want your processes for like motors and engines and things to be repeatable, okay? You want to get back to your original state so you can go around again. If you only do it once, it's not very useful, it's not very sustainable, okay? You won't be able to get that much energy out of the system. So you want processes to be cyclical. So all engines have a cycle, okay, that you can draw on a PV diagram, and then you can figure out how much work you can get out of it by integrating, okay? So that's, heaters, car engines, refrigerators, all of those things have cyclical processes, all right? All right, so let's go back to these different types of thermodynamic processes and fill in some of the, oh yes?
Yeah, I have one question. Why is it just on the inside and not the whole area underneath?
Oh, that? So it's because you see how there's like you could put dots here and here.
Oh,
So you want to integrate from here to here,
Mm-hmm.
and then you integrate from here to here, and you add them together. But this one should be positive. This one will be negative because you're going the other direction. So when you subtract them, it just gives you what's inside.
Oh, I see. Okay.
Yeah. So like that's what that visual looks like. So you integrate this way, and then you integrate that way. When you add those together, it's always going to be just the stuff inside
Okay.
the loop. Okay?
I
Yeah.
see the cool function now.
I animated it. So an isochoric process, that means constant volume. Okay? If we want to figure out the different points from here to here, we can use our PV equals nRT relationship. We know that volume stays the same, N stays the same, and R stays the same. So the only variables we need to worry about are P and T. So that means P1 over T1. So if you know the pressure and temperature here, and you know either the pressure or the temperature here, you can calculate what you're missing. Okay, so to go from here to here, you use this. All right, what do we know about the work? What's the work here?
0.
0, right? The integral of this is 0. Okay, so the work's 0, which means change in thermal energy is equal to Q, equal to the heat. All right, how do we calculate the heat for a constant volume process? We talked about this a little bit, but we'll go into more detail later. Heat for a constant volume process is NCV delta T. Remember, this is like NMC delta T, but for gases. Okay, this is for ideal gases. So for ideal gases, you can calculate heat for a constant volume process, and you can calculate heat for a constant pressure process. If it were constant pressure, this would just be CP delta T. It's a different constant. Yes.
The C and VCP stuff's gonna be given, right?
Yeah. Or at least it'll tell you if it's a monatomic or diatomic gas, because remember you can calculate that by figuring out the degrees of freedom. Right. You can write that down, right? There's only 2 numbers that you have to know, but it'll probably be given.
And that's for a constant what?
Constant volume.
Okay.
Okay, so that's specific to a process like this. So Q is NCV delta T if it's a constant volume process. Okay, so now you can calculate all the things, right? All of the things that you need to do the first law, because we know Q is this. We know if Q is this, then so is change in thermal energy, and we know work is 0. Okay. All right, let's talk about an isobaric process. That is constant pressure. So if you want to if you know stuff about this point, right, you only need to know P and V and T, to go back and forth between that point and that point. So remember, we have PB over T between all of our points. We can get rid of P because we know P is the same. Okay, so this is V1 over T1 is equal to V2 over T2. That's a good way to figure out what's going on between those two things. What's the work here?
The integral.
But how do you get, like, it's pressure, it's base, which is delta V, times height, which is P. So P delta V. Okay, work done by the system should be P delta V. In this case, is it positive or negative? Positive. Work done by the system here is positive. Work done by the environment would be negative. Okay, so we use this. We can't get rid of any of these things. None of these things are zero for an isobaric process. So this is Q minus work system. But what's Q if we have a constant pressure process? Yeah, NCP delta T. Okay? And it turns out thermal energy always, always, always is NCV delta T. So even if it's not a constant volume process, this is still true. Okay, so you can figure out all of these things. Here's how you figure out work. Here's how you figure out heat. Here's how you figure out change in thermal energy.
So that's always true for thermal energy?
Yeah, this is always true. For any process, not just constant volume or constant pressure, for isothermal, for any random process that's not one of these specific stated things, okay? Yeah. All right. So these slides are very important. You should probably write down the stuff on these slides on your cheat sheet, okay? Isothermal process, that is constant temperature, all right? So if we want to go back and forth between this point and this point, we know P1V1 is equal to P2V2 because we can get rid of the temperature part. How do we figure out the work? What's the work going to be? It's the area under the curve, but let's talk about what that actually looks like. So, we know work is going to be P dV. Okay? If we know that we have PV equals nRT, we want pressure in terms of volume. So pressure becomes nRT over volume. But what do we know about nRT in this case? Does N change? Does T change? And R is a constant. So that whole thing is constant. Okay, so when you plug this in, this becomes nRT over V dV. You take this out, nRT comes out, and you end up with dV over V. Okay, what does this integral give you? And this goes from V1 to V2. What's the integral of 1 over x? Yeah, ln, natural log, right? So this becomes nRT, natural log of V from V1 to V2. Okay, so that goes together. So that is our work. Okay, nRT, natural log of V from V final to V initial. Okay. What do we know about change in thermal energy for a process like this? 0, right? Temperature doesn't change, so thermal energy doesn't change, and the change in thermal energy is 0. Oops. Go back. Go back. So that means our Q is equal to our work. So even though we don't have a specific Q, right? Because remember, the Q's we can calculate are constant volume and constant pressure. So we can't easily calculate Q here independently, but we know it has to be equal to this. All right? Okay. I think we'll go through this one together, just in the interest of time. Yeah, we need to. All right, so we want to calculate and compare how much work is done in the following two cases. So we have 1 mole of gas initially at STP that's isobarically expanded to twice its volume, and then process B initially at STP goes through an isochoric process in which the pressure is doubled, okay? And then undergoes an isothermal expansion in which the volume is doubled and the pressure returns to its initial value. So I'm going to draw this, because that'll make more sense. So here's our PV diagram. Okay, we're going to start with process A. So we have 1 mole of gas initially at STP. So let's start here. This is the same for both things. Okay. So what is the pressure that it starts at? Yeah, one atmosphere, or 101, right? Kilopascals. And meters, if our volume is in meters cubed, what do we start at for 1 mole of gas? You can always calculate it.
For what?
So if we have 1 mole of gas at STP, it always has the same volume. 0.0224 meters cubed. Okay. So we're always starting there. And so this one is isobarically expanded to twice its volume. So first process takes us here. What's the volume? Okay, so that's our first process. Call this process A. Okay. Process B is a little bit different. The same gas, we start at the same point, right? So this is still point 1. Let's say initial, and this is final. Okay. But this time, we undergo an isochoric process where we double the pressure. So what's the pressure going to be? 202. So that means we double the pressure. Here's our intermediary step. And then we isothermally, from the initial. Then we isothermally expand it so it goes to the same endpoint. Okay, so this is process B, right? And we want to calculate the work for each of these things. Okay, so let's start with the work for this. How do we get this? So work A. This is the work done by the system. Okay, what's that going to be?
Base times height.
Yeah, base times height. Okay, what's the base?
0.024.
This is
224.
P delta B, right? So pressure, that's 101 times 10 to the 30 pascals, and volume should be 0.0224 meters cubed. Okay, so the work done by process A, that should be 2,270 joules. Right. For B, do you expect the work to be bigger or smaller?
Bigger.
Bigger, right? Because it has to be all of this. You can see that volume is going to be larger. The area it takes up is larger, okay? So what's the work done from here to here?
2 and 2.
From here to here?
Oh, I'm sorry. 101 times 10 to.
No, what's the area from here to here?
0.
0.
Oh, 0.
Okay? Then we have to calculate the work done from here to here.
Mm.
Okay? What's the work done by an isothermal process? That.
Mm.
Right? So that's going to be nRT, okay? Natural log of volume, this volume over this volume. If you divide this by this, what do you get? 2. Okay? We know there's 1 mole of ideal gas, how do we figure out T?
Well, it starts at 270 Kelvin.
Here's a neat trick, okay, right? We have PV equals nRT. If this is constant, this can be P initial, V initial, or it can be P final, V final. It doesn't matter. Okay, so we can just pick either this point or this point. We don't even have to calculate the temperature, and use just multiplied P and V together. So that can either be 101 times 0.448 or 202 times 0.224, and you'll see those will give you the same answers, right? So you just pick either this or this and calculate PV. Should be the same as nRT. All right. So this is going to be P final, V final, natural log of 2. So that's going to be pressure is 101 times 10 to the third pascals, 0.0448 meters cubed, natural log of 2. We expect this number to be bigger than that number, and it is about 3,000, so 3,140 joules. Okay? All right. Any questions about that? Remember, when we calculate the work, it's just the area under the curve. Okay, and the way that we know what the work is under an isotherm is, remember, an isotherm is just a constant times 1 over V. Right? Or you can just memorize that. That's always true for an isotherm. Yes?
Where'd you get the ln of 2?
So remember,
Well, the 2 part mainly.
this becomes nRT, natural log of V2 over V1. We know the volume doubled, so that this divided by this,
Oh,
so that should be 2. Yeah. All right. Okay, so let's talk about the thermal energy. So the internal or thermal energy of an ideal gas depends only on its temperature. So we know there's some relationship between delta T and delta ETH, okay? And it turns out this is the relationship. NCV, the C, the heat capacity for a constant volume change, times delta T. Okay, so this is the constant that connects this to this. All right, and this is always true. Remember Q, this term is true for Q for an isochoric process. But for an isochoric process, work is 0. So this is true for E thermal and for Q for an isochoric process. For something like this, for an isothermal process, right, this is true for E thermal but not for Q. Right? For an isobaric process, this is true for E thermal but not for Q. Right? So this is always true for your change in thermal energy, but it's not always true for your heat. Okay? And let's talk a little bit more about heat capacities. So here's some molar heat capacities for solids, right? Remember, we talked about this. Q is equal to mc delta T. You can change back and forth and make this nc delta T just by knowing the molar mass. Okay, remember, this is the number of moles. This is molar mass. You can go back and forth between number of moles and mass using molar mass. All right? So this is a chart that sort of puts these together. We talked about this a little bit in a previous chapter. Not super important. The main takeaway is that solids have different heat capacities. You can either do them in terms of mass or you can do them in terms of moles, depending on what you want to do. So Q is always equal to some sort of NC delta T. Now for gases, it doesn't just matter the material, it matters what process you go through, which is why we have a different C for a constant volume process than we do for a constant pressure process. Okay? So in an ideal gas, let's say we have these two isotherms. Okay, and what do we know about the temperature along this isotherm? Constant. Okay, and the temperature along the other one, constant. So if you go this way, right, the heat here is NCV delta T. This is the molar heat at constant volume. Okay? If you go this way, you have the same temperature change, but you have a different heat transfer. okay? So this would be NCP delta T because this is the constant pressure, okay? So the change in heat, the change in heat is different, right? The heat transfer is different. The change in temperature is the same. And what this says is there's two different ways to go from one temperature to another. Actually, there's more than two, but there's two that we get nice calculations for the heat. Because you could also draw any line that goes from this isotherm to this isotherm is acceptable as long as you can create it in the physical reality. Okay, so those will all have the same change in temperature, but they won't all have the same change in heat. Okay, so if you look at this, the temperature change is the same, which means thermal energy should be the same for both, right? So temperature change, same change in temperature, same change in thermal energy. All right, in an isochoric process, your work is 0. All right, in an isobaric process, your work is this. Okay, just the rectangle under the curve. So, here's some math that you don't need to necessarily know, but if you put all this stuff together, it turns out, okay, since you're not changing your thermal energy, you end up with this relationship, right? This, CV, is equal to CP minus R. What's R? That's that constant, 8.31. Okay? So that means if you know CP, you can just subtract 8.31 and get your CV. Okay? So your molar heat capacity, they're related, which makes sense because they're for the same gas. Okay? So you can always rewrite this, and you can see, let's say for this monatomic gas, CV is 12.47. What's CP? 20.7. So this plus 8.3 should give you this. Okay, and that should work for all of them. All right. So the other thing we do with these heat capacities is we use this ratio, and we call it gamma. It's basically like a squiggly thing. Okay. We know because this is this plus 8.3, CP is always greater than CV. So what does that tell us about gamma? If this is always bigger than this, what kind of fraction is this? That's improper, right? Which means this value is always greater than 1. Okay, so gamma is always, always, always greater than 1. And here are some various gammas. For monatomic gas, we have 1.67. For diatomic gas, it's 1.4. And for polyatomic gases, it's messy, but it's around 1.3. Okay, so this actually ends up mattering when we talk about, we're going to talk about next, which is the adiabatic process. Okay, so we know processes where work is 0, that's isochoric. We know where change in thermal energy is 0, that's isothermal. The adiabatic process, guess what's 0? Heat. Okay? We're going to skip this. We're going to skip this one just because we are running out of time. But remember, change in thermal energy is always this formula, okay? NCV delta T. If you ever want to calculate change in thermal energy, you can just plug this in, all right? It doesn't have to be, I know this, you know this is for a constant volume process. That's only if you're calculating heat. If you're calculating thermal energy, this is always, always true, okay? So let's talk about the adiabatic process. So, adiabatic process means no heat transfer. Remember, an isothermal process usually has to happen very slowly. The best way for heat to not be transferred is to do stuff really, really fast. So a good example of an adiabatic process is like an explosion, right? There's not time for heat to transfer from one place to another right as the explosion's happening. That is an adiabatic process. So for instance, in your car, you put vapor gasoline into the cylinder, then what do? You ignite it, okay? That is an adiabatic process, all right? The heat doesn't have time to go anywhere because it just explodes and it happens really fast, Okay, so things that happen really fast are usually adiabatic. Things that happen really slow are usually isothermal. Okay, so if you're reading a problem and it says this thing happens really fast, you can guess it's probably adiabatic. All right.
That's funny.
So- So opening a can, right, a carbonated can, that's an adiabatic process, right? You're changing the volume really quickly, but there's no time for heat to go in and out of the can because it happens fast.
That is weird. It's weird that it's water coming out of that Pepsi can.
It's probably healthier. Okay, so an adiabatic process looks like this. The curve looks like this. And what does this tell you? It's steeper than an isotherm, and it crosses the isotherms. So that means you have a change in temperature, right? Which means you have a change in thermal energy. But what's zero?
Heat.
Heat transfer, Q,
Oh, yeah.
right? So Q is zero. If you want to go from one point to another, you have to use this. You can't make any of these zero because none of these variables are constant, right? This pressure changes. You can see pressure changes, volume changes, temperature changes too. So we don't get to simplify that too much, okay? But Q is equal to zero, which means if you know the change in thermal energy, that's going to be the negative of the work of the system or equal to the work done by the environment, okay? This is where gamma comes in. It turns out, I won't go through the whole derivation because we're running out of time, but it turns out if you have the pressure here, right? So this is pressure 1, volume 1. Pressure times volume to the gamma. Remember, gamma was either 1.67, 1.4, or 1.3, depending on whether it's a monatomic, diatomic, or polyatomic gas.
Will that be given to us? Or is that a...
You need to know those three, and it'll tell you if it's a monatomic, diatomic, or polyatomic gas. So, like, for instance, if it says that it's helium, what kind of gas is that? Monatomic. Okay, if it says that it's nitrogen, what kind of gas is that? Diatomic. And I think if it's polyatomic, I'll just say it's polyatomic. Yeah. If you haven't taken chemistry and you're stuck on which one it is, just ask me. But if it's anything on this will be showing. If it's anything on that far right column, that's going to be monatomic. If it's anything this way, that'll either be diatomic or polyatomic. Okay. All right. So this is all you need to write down on your card for an adiabatic process, aside from what it is. Okay. These are all the formulas you would use to calculate a diatomic process. Now, calculating the work, that's a little bit trickier because you have to actually go back to P dV. Then you solve this for V. There's a gamma, and the integral gets ugly. Okay, so it's usually easiest when you're doing these problems, in this class at least, to calculate the thermal energy and just know that it's equal to the work. Okay, all right. There's our adiabatic process. Shall we do a problem?
What does T1V1 gamma minus 1 give us then?
T1 V1 gamma minus 1? That's how you go back and forth between, like if you know the pressure and volume at the beginning, and you, like let's say you knew pressure and volume here, and they gave you the pressure here and they wanted you to calculate the volume, you'd use this.
Okay.
And so this would be like, let's say this is a monatomic gas. This would be pressure. So let's say it's atmospheric pressure, so 101 kilopascals times volume. Let's say it was 0.0224, but it would be 0.0224 to the 1.67.
Oh.
So you'd have to say 0.224 to the, and so people screw this up a lot because a lot of you guys don't remember how to do exponents that aren't like a 2 or a 1/2. So remember how to add and divide things with exponents, right? If you don't remember, please review that. I'm sure Khan Academy has a nice video on it or something, okay? But you're going to want to be able to go back and forth using these gammas. And gamma, remember, has 3 possible values. If it's monatomic, it's 1.67. If it's diatomic, it's 1.4. And if it's polyatomic, it's about 1.3. Okay? All right. Oh, we have an extra 15 minutes. It's Monday. Cool. All right, let's do a problem. So I'll draw this out and do it. Just read through it and then we'll do it together.
Is that compression ratio, is that gamma?
The
Compression ratio.
no. It's V final over V initial. I don't know why it tells you that the compression ratio is 10 because you can it's just this divided by this. So
So you go a lot more
it's
better.
kind of misleading. So here's what this looks like visually. So here's your initial state, right? You have atmospheric pressure and 500 centimeters cubed volume, okay? So you should be able to calculate temperature from that if you need to. And then, it gives you the temperature. So this starts at T1. Should have written that. So T1 or T initial, that's going to be 30 degrees Celsius. What's that in Kelvin? 303 Kelvin. So we know the initial pressure, volume, and temperature. Okay? That means we can calculate N, which we'll need later. So we'll start by doing that. So N, that's going to be PV over RT. So that is pressure, which is 101 times 10 to the third pascals. Volume, which is 500 times 10 to the negative 6 meters cubed, because we needed meters cubed. And then R is 8.31 joules per mole Kelvin. And temperature is 303 Kelvin. This should give you an N of 0.0201 moles. Okay, so that's your N. If we want to figure out volume and final temperature and final pressure, we can use these two equations. Okay, remember this is always true if you're going from point to point on a PV diagram. This is true for an adiabatic process. Okay, so we want to figure out the final pressure. So pressure final, that's going to be equal to volume initial over volume final to the gamma times pressure initial. Okay, so so volume initial, is that bigger or smaller than volume final? Smaller, right? So this should be 1/10, right? Or you can plug in, right? This is volume initial, no, because that's backwards. It's 10. So this is going to be 500 divided by 50, right? We don't have to convert to meters cubed because it's a ratio. So this is going to be 10, that's the compression ratio, to the gamma. What gamma do we use? 1.4 because it's a diatomic gas. So this is to the 1.4. Okay, so 10 to the 1.4 times the pressure, which is 101 times 10 to the third pascals. Okay, so that should give you a final pressure of about 2.5 times 10 to the sixth. Pascals, so that's about 250, is that right? No, about 2,500 kilopascals. Okay, because you have to move the 3, move it over, you still have 3. All right, so that's your final pressure. If you want your final temperature, you can use this. So temperature final, that's going to be pressure final, volume final over pressure initial, volume initial times T initial. Okay, so now we know all of those things. This is 101 times 10 to the third. This is going to be 500 times 10 to the negative sixth. And this is 2.5 times 10 to the sixth. This is 50 times 10 to the negative sixth. What? Yeah. 101 times 10 to the third. 500 times 10 to the negative sixth. 2.5 times 10 to the sixth. 50 times 10 to the negative sixth times 303 Kelvin. That should give you a different temperature. That's going to be 761 Kelvin. Which means this is 761 Kelvin because this is your isotherm you end up on. Okay? So here's your final pressure, your final temperature. That's part A. We already drew the diagram. That's part B. We want to know how much work is done to compress the gas. How do we get work? Do we want to do an integral? Can we get away with not doing an integral? What do we know about an adiabatic process? So Q is 0.
So it's same.
So that means change in thermal energy is equal to work done by the environment.
So we just do the change in
And we know change in thermal energy, NCV delta T. Okay, we know delta T, we know N, and CV is a constant that we can figure out for a diatomic gas. Okay, so CV, well, it's given, it's 20.8, so we end up with 0.0201 moles times 20.8 that's in joules per mole Kelvin, times the change in temperature, which is 761 minus 303 Kelvin. All right, and that's going to give us some number in what units?
How did you get that
Joules.
that mole?
So 192 joules. The mole?
Oh, we found that?
PV equals nRT. So 192 joules. Okay. And for some reason this is turned off. All right, so that's a good candidate for like a test type question. All right, so the next chapter, that's the end of this chapter pretty much. There's a couple more slides on how to go through these, but they're just